Welcome to this video on quadratic variation of Brownian motion. We will explore this fundamental property, provide rigorous proofs, and discuss its significance in stochastic calculus and applications. Let's begin with the definition of quadratic variation. For a stochastic process, the quadratic variation measures the accumulated squared differences over time. Formally, it is defined as the limit of the summation of the squared increments as the partition of the time interval becomes infinitely fine. This concept is crucial for understanding the behavior of stochastic processes. Before diving into the quadratic variation, let's recall the key properties of Brownian motion. It starts at zero, has independent increments that follows a normal distribution, and its paths are continuous but nowhere differentiable. These properties will be essential for understanding why Brownian motion has such unique quadratic variation properties. Our main theorem states that the quadratic variation of a standard Brownian motion over an interval, let's say from 0 to t, equals the length of it, t. This is a remarkable property that distinguishes Brownian motion from deterministic process. For smooth functions, the quadratic variation would be 0, but for Brownian motion, it equals time itself. This convergence is not just improbability, it holds almost surely. Here is our approach to proving that the quadratic variation of a Brownian motion equals time. First, we will show that for any partition, the expected value of the sum of squared increments equals t. Then we will demonstrate that the variance of this sum converges to 0 as the partition becomes final. Finally, we will use the Chebyshev's inequality and the Borel-Cantelli lemma to establish almost sure convergence. For the first part of our proof, we calculate the expected value of the sum of squared increments. Using the independence of Brownian motion increments, we can separate the expectation of the sum into a summation of expectations. Since each increment follows a normal distribution, its second moment equals its variance, which is the time difference, ti plus 1 minus ti. Summing this up gives us exactly t, the length of the interval. For the second part, we need to show that the variance of our sum approaches 0 as the partition becomes final. We use the fact that for normal random variables, the force moment equals 3 times the squares of the variance, so 3 sigma to the power 4. This allows us to calculate the variance of each squared increments, so which is equal to the expectation of its force moments and minus the square of the second moment. And in the end, we get that actually the variance of the squared increments is 2 times ti plus 1 minus ti squared. So this leads to that should the total variance is bounded by a term that includes the maximum partition width, which approaches to 0 as the partition becomes infinitely fine. So this converges to 0 as this size tends to 0. To complete the proof, we apply the Chebyshev inequality, which bounds the probability that our sum deviates from t by more than any positive amount epsilon. Since the variance approaches 0, by carefully this probability also approaches to 0. By carefully constructing a sequence of increasingly fine partitions and applying the Borel-Cantelli lemma, we can upgrade this convergence in probability to almost sure convergence, establishing that the quadratic variation equals to t with probability 1. The quadratic variation property is fundamental to stochastic calculus. Explains why classical calculus rules do not apply to Brownian motion, and it makes necessary to develop the Ito's calculus. The famous Ito formula includes an extra term involving the second-order derivative, which arises precisely because the quadratic variation of a Brownian motion is not zero. This property is also essential for defining stochastic integrals and developing the theory of stochastic differential equations. The concept of quadratic variation extends to other stochastic processes related to Brownian motion. First, adding a drift term does not change the quadratic variation. By scaling Brownian motion by a constant scales its quadratic variation by the square of that constant. For general Ito processes, the quadratic variation involves integrating the squared diffusion coefficients. We can also define quadratic covariation between different processes, which is crucial for multivariate stochastic calculus. The quadratic variation concept has numerous practical applications. In finance, it's used to estimate volatility from market data and plays a crucial role in option pricing and risk management. In statistics, it helps with inference for diffusion processes. Engineers use it for filtering problems, and physicists apply it in models of random phenomena. The theoretical properties we have proven has far-reaching practical implications across multiple disciplines. In conclusion, we have proven that the quadratic variation of Brownian motion equals time, a remarkable property that distinguishes it from deterministic processes. This property forms the foundation of stochastic calculus and has wide-ranging implications in theory and practice. Understanding quadratic variation is essential for anyone working with stochastic processes, whether in mathematics, finance, physics, or engineering.